Your query is slow. You add an index on the column you're filtering by, the query gets faster, dramatically faster. Problem solved. A week later, a different query slows down. You add another index. It helps. A month in, the table has 8 indexes, writes are noticeably slower, disk usage has doubled, and one of your original queries is somehow slow again. Nothing you added was wrong. And yet, an index is not free. That sentence sounds obvious, and almost nobody acts like it. This episode is what an index actually is, what it actually costs, and why add an index is the reflex that gets you into most of the messes it's supposed to solve. Start with what an index actually is. When you create an index on the email column, Postgres builds a second data structure alongside the table, usually a B tree. A balanced tree of nodes, each node a small sorted list of keys pointing at either more nodes or, at the very bottom, physical row locations. To look up a specific email, Postgres starts at the top, follows the pointer to whichever child would contain it, and repeats, walking down maybe 3 or 4 levels for even a huge table because each level branches wide. That's the win. A lookup on a 50 million row table becomes 3 or 4 small reads instead of a full scan of every row. This is the reason indexes exist, and it's a genuinely enormous speed up. If the story ended here, add an index really would be the answer. The story doesn't end here. Here's cost number 1, and it's the one everyone forgets. The index has to stay accurate. Every insert writes the row to the table and also walks down every index and inserts a new entry at the right place. 10 indexes means 10 extra small writes per row. Every update that changes an indexed column has to update those entries too. And because EP1 established that update writes a new copy at a new physical location, the old index entry now points at a dead tuple, and a new entry needs to point at the new location. So the first hidden cost, an index makes reads that use it faster and makes every write slower in proportion to how many indexes exist. 8 indexes is 8 times the write amplification. Just add another index is a decision with a tail, not a free win. You're adding a permanent tax on every future write. Cost number 2 is what happens to the index over time. From F1, update doesn't remove the old row, it marks it dead. That dead tuple is still visible through the index until AutoVacuum cleans up. The old index entry is still there, still walked over during traversal. The same bloat mechanism that makes tables slow makes indexes slow. And worse, indexes tend to bloat faster because updating the same handful of rows over and over churns through index entries even when the indexed column itself didn't change. AutoVacuum cleans this up on a schedule, same as it does for tables. But bloated indexes are the reason people occasionally have to run REINDEX, the index equivalent of vacuum full, rebuilding the whole thing from scratch. It works, and like vacuum full, it takes a heavy lock, which means it's not something you casually do on a live production system. Cost number 3 is subtler, and it's where indexes turn actively harmful. A wrong index is worse than no index. Here's what that means. When Postgres plans a query, it looks at what indexes exist and estimates the cost of using each one versus just scanning the whole table. If you have an index on a column where 90% of rows have the same value and you query for that value, the optimization is to use the index to find 90% of the table, then go back to the actual table to read every one of those. That's slower than just scanning the whole table in one pass, and a good planner will correctly skip the index. But it still had to consider it, and it still had to update it on every write. An index that never helps a query is pure cost, and an index that sometimes helps and sometimes gets ignored is worse than pure cost. It's cost you're paying for a benefit you rarely receive. So how do you know which indexes are earning their keep? Postgres tracks it. There's a system view called PG stat user indexes that records how often each index has been used to satisfy a query. An index with a scan count of 0 has never been used since the statistics were last reset. It's pure overhead. Dropping it is almost always the right call. One more cost, because it comes up right when you least want it. Every index has to be built, and building one on a large table takes time and takes locks. A regular create index locks the table against writes while it runs. On a busy production table with 50 million rows, minutes of downtime for what you thought was a routine change. Create index concurrently exists exactly for this. Slower to build, more resources, can fail partway through, leaving an invalid index behind, but it doesn't block writes. Almost every production index should use it. Almost every "we took the site down at 3 a.m. story involves someone who didn't. Left panel, create index, continue. Pull all of that together. An index is a secondary sorted data structure that turns full table scans into 3 or 4 hop lookups. It costs write amplification, roughly proportional to the number of indexes, index bloat that auto vacuum has to keep up with, a permanent tax on every write for every index, whether or not it's ever used, and a real production risk when creating one on a large, busy table. So the honest version of add an index is first, check whether the query actually needs one, then check whether an existing index could cover it, then check whether the column is selective enough that an index would help rather than be ignored, then build it concurrently, then weeks later look at PG stat user indexes and drop the ones that never got used. That's the whole workflow, and it's why add an index is the reflex that seems free right up until the moment you have 8 of them and every write is paying tax to all of them. A closing strip. Index equals sorted side structure. Write cost equals number of indexes. Bloat plus auto vacuum. Unused indexes equals pure tax. Build concurrently or take downtime. Next time, you write a query, press enter, and Postgres does something you didn't ask for. It ignores the index you built for it. It reads the whole table when it should have done a lookup. And sometimes it's right to do that. The planner and the beautiful catastrophe of a query that ran fine yesterday and terribly today because nothing in your code changed.